All right, everybody, welcome to our 8th lecture of the semester here in Calculus 3. So last time we started talking about vector valued functions where we input a number or a parameter, usually denoted by t, and then out pops a vector. And we saw that the algebra and calculus involving these vector valued functions is exactly what you'd expect. Most of the time you just do the same thing to each different component. So yeah, thankfully that's not too complicated. And also it had a lot to do with parametric equations, which we also seen in Calc 2. Now today we're also going to kind of continue a sort of a pseudo Calc 2 review because this may look a little bit familiar. We're going to talk about arc length today, but then we will be branching into something new called curvature as well. So we're going to continue talking about these curves in three-dimensional space. All right, so let's talk about arc length. So arc length is just a fancy name for how long a curve is. And for a two-dimensional curve, or rather a curve in two-dimensional space, if we have our x being f of t and our y being g of t, like parametric equations from last semester, then the arc length is the integral from a to b of the square root of these guys squared. Notice that these are derivatives here. All right, now why is this true? Well, what we could do is we could technically break up this curve, for example, into tiny little triangles. And if we blow up these triangles like this, and this height is a tiny change in x, and this height is a tiny change in y, then we can approximate the length of this curve right here with something called ds, where ds is dx squared plus dy squared. And then we take, ds is the square root of these guys because of the Pythagorean theorem. And then we effectively divide both sides of this by dt, and we add all of them together, or we integrate them. So that's where this formula ends up coming from here. It's effectively an application of the Pythagorean theorem. Okay, well, that was in 2 dimensions. How is this going to work in 3 dimensions? Well, it's going to work exactly the way you'd expect. So we have our x component squared here, or the derivative of the x squared, the derivative of the y squared. And all we're going to do to extend it into 3 dimensions here is, oh, I did mix them up. Whoops. Let's go back to algebra. There, dx dy, there we go. All right. So this time our formula is going to be the square root of f prime of t squared g prime of t squared. And then you could probably guess what's going to come next. We're going to have h prime of t squared, where this is now the rate of change of the z component as well. So this is going to be our definition for arc length in 3 dimensions. And if maybe you have some bizarre application where you're looking for arc length in 4 dimensions or 5 dimensions or 100, it's just going to be exactly the same. You're going to keep adding the square of the derivative of your components. All right, now there's actually another way that we can view this right here. So back in Calc 2, when we did the t derivative of s, and we got this, there was a special name for this, right? What was the name of this quantity? Does anyone remember? It's a physics term, and it's a rate of change of a position. It's not quite velocity, because it's going to be the magnitude of something. It's going to be the speed. So technically, so this is the speed right here. So if we put in the magnitude of our position right here, or the derivative of the position, then this will also give us the same thing. So this is the speed. And if we integrate the speed function, then we end up getting the distance function. Kind of like how if we integrate velocity, we end up getting displacement. And note that this is always greater than or equal to 0 because we're integrating the square root of something right here. And that's never going to be negative. So this integral has to be greater than or equal to 0. All right, that's all well and good. That makes sense. Let's go ahead and practice this right here. So let's calculate the arc length of the curve. R of t is this right here. And by the way, I think for those of you who had me in Calc 2, I mentioned this, but you could also, I guess I just wrote it. You can imagine this as the distance a particle travels if the particle has this position function right here. That's another way you can imagine the arc length integral. All right, so let's go ahead and do this here. So we want to do our arc length. So our integral, we want to do this from 1 to e. And then we have the square root. Now, this is f of t, g of t, and h of t. So in order to use the formula up here, we need to have the derivatives of this. So f prime of t, we do a power rule and get 2t. G prime of t, we do a power rule and get 2. And then h prime of t, we do the derivative of natural log, which is 1 over t right there. All right. So what's going to happen is we're going to square each of these. You can't forget to square them, and we're going to put them inside here. So 2t squared will be 4t squared. 2 squared is 4. And then 1 over t squared is, well, 1 over t squared. Okay, so now we need to do this integral right here. We set up our problem, now we need to do this integral. Now we look at this and maybe if it's like this, we could kind of dig up our trig sub memories and try to attempt to do that. But we have this 1 over t squared here as well. So this is kind of making things a little bit difficult here. But there's actually some algebra trick that we can do to simplify this. Does anybody see, this is actually going to factor. Does anyone see what this is going to factor into? Let's see here. So what we could do is we can, you could either kind of just see it a little bit, but if you don't see it, that's okay. We are going to multiply a top and bottom by t.
Professor, can you move it up, please?
Oh, yep. All right. So let's see. We have this. Now, when the t moves inside the square root, it's going to become t squared. So we're going to have square root of 4t to the 4th plus 4t squared plus 1. Okay. Okay, now that it's written in this way, what we could do is we could factor it as t squared right here. So we could pretend like this is the normal variable squared, this is the normal variable, and then we have a constant. So if we factor this here, it's going to factor into 2t squared plus, wait a minute. Yeah, no, that's right, that's right, what am I saying? Yeah, there we go. All right, so we factored that. And then now we have the square root of something squared, so we can have that cancel. And then we could divide by t. Okay, so there we go. So we simplified our integral into something that we are able to do here. All right, now one thing for future reference is that if we see something like this where we have a positive power, just a constant, and then the negative version of that power, you can immediately factor it into this squared. So you can immediately do that in the future. You can kind of skip from this step here to maybe this step, but we put the t inside here. This is actually a pretty common situation where we have a positive power, a constant, and then the negative version of that power as well. All right. So anyway, so we have this here, and now we're going to do the integral. So we have t squared plus natural log of absolute value of t from 1 to e. And then we're going to go ahead and plug this in. We have e squared plus natural log of e. And then we subtract 1 and 0. And natural log of e is 1. So this and this go away. And we end up with e squared as the length of this curve right here. All right, so there we go. So sometimes we might need to do a little bit of factoring on something like this. And remember, something like this, let me write it down here so you guys remember. This 4t squared plus 4 plus 1 over t squared will factor into 2t plus 1 over t squared. So however it would factor like this, you effectively just divide it by a t, and this is what we're going to get here. Is there a good online resource for graphing these curves? Yeah, Desmos can definitely graph parametric curves, but I'm not sure if they do it in 3D. Has anyone tried it in? They don't do it in 3D? Okay. Oh yeah, there's GeoGebra, that's right, yeah. So Dr. Huang suggested GeoGebra. Wolfram Alpha will also do this, but sometimes their scale is kind of weird for curves. So I would probably just recommend GeoGebra. All right, so there we go. We got E squared right here. All right. Let's see here. So now let's talk about something called the arc length function. So the arc length function is very similar to the actual arc length. What it does is it tells you if your particle's moved a certain amount of time, how far has it gone? Or if you've moved a certain amount of t values along your curve, how far have you gone? So that means that this is going to be the integral from a to t. So we stop at whatever time we put in. And then we have the square root of f prime. Now, we usually use s as a backup t, but we already have an s right here. So I'm just going to write u. Yeah, du is, remember, du is what's called a dummy variable right here. It's because effectively, once we're going to integrate this, we're going to stick the t in place of the u right here. So what this is saying is how far we have gone after time t. That's what this function represents. All right, now if we have this function and we take the derivative of it, we're doing the derivative of an integral, right? And we have our top variable matching the variable we're doing for our derivative right here. I'm going to zoom out so I don't have to keep shifting. Oh, that's as zoomed out as it gets. There we go. I don't think that changed very much, but we'll just go with it. All right. So if we do the derivative of this integral right here, the derivative and the integral more or less cancel out, and we just plug in t for all of these. So we get the square root of f prime of t squared, and g prime of t squared, and h prime of t squared. And note that this is the magnitude of your derivative of your curve. And remember, the name for this is going to be speed right here. Is a always 0? No, a could be any value you want. So you can imagine that the arc length function represents how far you've gone from time t equals a to your time t equals t, where you could put it any number you want for t. All right. So let's see here. How is this going to be speed? Well, remember that r prime is f prime of t, g prime of t, and h prime of t. If we find the magnitude of this, we'll end up getting this equation right here. And the absolute value of velocity is going to be speed. Okay. Now, sometimes what we want to do, so usually when we start off with a problem, we start off with our curve, and it's given as a function of time, or more generally, the parameter t. But sometimes we would like to change our vector valued functions to be dependent on arc length as well. So rather than saying, I'm going to input an amount of time that I've gone, you're instead going to input the amount of distance that you've gone instead. So rather than saying, oh, I want to see how far I've gone after 2 seconds or something, you say, oh, I want to see where I am after 1 meter. Okay, so how are we supposed to do this? How are we supposed to switch to have our variable be from time to being distance, or t to s? Well, we've solved for t as a function of s. So we go up here, we do whatever this integral is going to be, and it'll be some function of t, and then we solve this 4t in terms of s. And then finally, we stick our new t value, which is now in terms of s, inside our original function. This is definitely more easily explained by an example. So let's take a look at an example of this. Okay. Oh yeah, sorry, there's an abbreviation here, with respect to. So effectively what we're doing is we're changing our curve to be with respect to length rather than time. All right. So what we're going to do here is we're going to apply this to the helix. So remember, the helix has a circle equation in 2 of its coordinates, and then it just has some linear value in the 3rd coordinate. So this circle is going to keep going up and up and up as t increases. So we want to reparameterize this by its arc length. And then using that reparameterization, we want to see where we are after we travel root 2 pi distance units, or maybe root 2 pi meters, rather than a certain amount of time. Okay, so the first thing we need to do is we need to define our arc length function. And since we're starting from 1, 0, 0, so this is the x, y, z value here, then what is the t value that matches up with 1, 0, 0? What t value do we put in here to get that? 0, that's right. So our bottom bound will be 0 here because we're starting from this point, which corresponds to t equals 0. And then remember, our top bound is going to be t right here. All right, and then we have the square root of a bunch of stuff. So if this is r, let's write out what r prime is going to be so we can fill in this integral. All right, so we have cosine here. So that means we're going to have negative sine of t right there. We have sine of t, we do the derivative of that and get cosine. And then we have t right here, we take the derivative of t and get 1. All right, now remember, the thing that goes inside the square root is the square of each one of these derivatives here. So for the first one, I square negative sine and I get sine squared. Not negative sine squared, the negative will square away right here. Then I add in and I have cosine squared. I think you guys can probably see where this is going here. And then I add in 1 squared, which is 1. Oops, these should not be t's. I'm so used to writing t. These should be a different variable, which I'm going to call u, because we have t up here. So we can't use this variable inside our integral because it's part of the bounds. Okay, now it looks like Tristan has the right idea here. 1 plus 1, last I checked, that's equal to 2. And where am I getting 1 plus 1? Well, we have a sine squared plus a cosine squared. We have a nice Pythagorean pair right here. So this is a fancy way of writing 1. So now we're going to use the fact that 1 plus 1 is 2. And we're integrating the square root of 2 with respect to u. All right, so this integral turned from somewhat scary looking to really easy, because now we just integrate a constant, and that means we just put the variable that we're integrating with respect to next to it. Okay, so we have our bounds from 0 to t, and then we're going to plug t in here. We're going to have root 2t, and then we're going to subtract and put 0 in there, but that's just 0. So this function, this arc length function, which started out looking really kind of complicated, ended up just being root 2 times t in disguise, meaning that however many seconds you go or however many time units you travel in this helix pattern, you can get your distance by just multiplying by root 2. Now remember, what we want to do, our goal is to have r depend on s, not r depend on t. Remember, this is our goal right here. And this is, someone just asked what reparameterize means. It means this. I want to have a function of s, of distance, rather than a function of time. So what I need to do the steps that we had on the previous page here. First, I solve for t in terms of s. Okay, so I'm going to do that. So I have s is root 2t. All right, well, this is very easy to solve for t. So s divided by root 2 will be t. Okay, then what I do, now that I've solved for t here, is every time I see a t in my formula up here, I'm going to replace it with s over root 2. So our second and final step here is saying that r of s, so now it depends on arc length, is going to be cosine of s over root 2 I hat, sine of s over root 2 j hat, and then s over root 2 k hat, right here. All right, so we have that. How do I find t equals 0 from this? I set 1 equal to this, 0 equal to this, and 0 equal to this. And t equals 0 is the only number that will satisfy all of those. Now there's one more thing we need to do. We need to find the position after traveling root 2 pi units. So that's effectively just finding r of root 2 pi, where now we're using our arc length r instead of our time r. So this is going to be cosine of root 2 pi over pi I hat. Same thing with sine here. Oh, sorry, this is root 2 in the bottom. And then root 2 pi over root 2 k hat. All right, so these will cancel out, and we end up with cosine of pi right here, and cosine of pi is -1. All right, we have sine of pi here when these cancel out, which is 0. And then finally, we have pi here for our last one. So this is going to be our position after we travel root 2 pi meters, or whatever our distance unit is going to be right here. All right. In general, reparameterizations are hard because you have to do an integral where you square a bunch of things and have a square root. So unless you have a bunch of sines or cosines or other things that cancel, it's not going to be easy to do this integral in general. So this is unfortunately, one of the easiest examples. Good news for you guys is that any examples that are harder than this quickly become impossible to integrate using known techniques. So they're mostly going to be kind of like this, the ones we're going to give you. All right, so that's enough about arc length. That's what we could do with arc length. Now I'm going to talk about curvature right here. So if C is a smooth curve defined by the vector function r of t, then the unit tangent vector is the following. We have r prime of t divided by the magnitude of r prime of t. And remember, this is the unit tangent vector. So what's the magnitude of this vector going to be? It's 1, right? Anytime something's called a unit vector, remember, it's going to have magnitude 1. So what does this vector do? This vector points in a direction of motion or change in r, if you're not doing physics. Okay, so effectively, this is just telling you where your curve is currently going. That's the significance of this vector here. Now, remember back in Calculus 1, I said that we're going to make a lot of analogies to Calculus 1, and here's another one. In addition to wanting to know the rate of change of your current function, you may also want to know the rate of change of your rate of change. And we could do the same thing with curves in three-dimensional space. So what we're going to do is we're going to try to come up with something that where the magnitude of which is going to be the rate of change of this with respect to the length. So we're going to call this thing curvature. And you can almost kind of imagine that this is sort of the three-dimensional version of concavity that we had before. It tells you effectively how bendy your curve is going to be. So what's the mathematical definition here? This is going to be the magnitude of the derivative of this guy, so the rate of change of our unit tangent vector with respect to s. Now note that this is respect to s right here. This isn't with respect to t. So this is telling you, like, if you go a certain distance along your curve, how much is the direction you're going in changing. It's not how you go a certain amount of time along your curve, it's a certain amount of distance. Okay, so this is the rate of change of the direction with respect to, so I'm going to use that WRT notation here, with respect to distance. Okay, what is the weird name? Yeah, this kind of looks like some bizarre K. Usually with handwriting, I write it like that. This is called kappa. This is usually called kappa right there. All right, so what we're going to do is yeah, a lot of kappas in the chat here. So we're going to compare curvatures of the following curves. Okay, so let's imagine that we're going along this straight line, right? So at each point, here is our direction vector. So how much is our direction vector changing as we move along this curve? Is the direction we're moving in changing at all? Yeah, it's not changing at all, so what's kappa going to be for this? It's not changing then. Yeah, that's right, it's going to equal 0. There is no change in our unit tangent vector. Okay, here we kind of have some change in our unit tangent. Like here we have it going that way, and then here we're going this way. But it's not changing too quickly. It's kind of slowly rotating as we move along this curve here. So this kappa, which here I'll call this kappa 1, this kappa 2. This is going to be some small value. We can't tell specifically what it's going to be without having a formula or something like that, but it's going to be relatively small. Now, if we look at this curve right here, we see that this is changing relatively quickly, our tangent vector, as we move along. So for this one, which I'm going to call kappa 3, this is going to be large. So if we were to compare the size of these, kappa 3 is greater than kappa 2, is greater than kappa 1, and kappa 1 is the only one we know specifically right here. This is going to equal 0 right here. Well, sometimes, yeah, kappa can be undefined. Yeah, we'll see a formula later where kappa can be undefined, where it's like twisting infinitely fast. Yeah, that is possible. Okay. Now, one thing to note, kappa is not quite the acceleration. So kappa is not equal to the magnitude of r double prime of t. So I just want to get this out of the way here. It's not exactly our second derivative from Calc 1, but it kind of plays a similar role to our derivative from Calculus 1. All right. So now, this is all well and good, but unless we want to reparameterize everything we're working with, this is not a very convenient formula to use. In fact, this is probably the formula that we're going to use the least for computing curvature. It turns out that there are other formulas that we're going to use for it. So our first formula for kappa that actually depends on time and not necessarily distance, so it's usually what we're given, that's going to be the magnitude of the rate of change of t, or unit vector, divided by the magnitude of r prime right here. And why is this true? I can explain that relatively fast. If kappa is dt ds, then what we could do is we could effectively divide the top and bottom by dt. And remember, it's not actually quite division, but you can kind of think of it that way. And then this top part is going to be the magnitude of t hat, or sorry, the derivative of t hat. And then the bottom, ds dt. What's ds dt? Remember, that's the magnitude of r prime. This is the speed right here, which is the magnitude of r prime. So that's where this formula comes from. And effectively, you just insert a dt right there. Where does this one come from? The proof of this one's messy. So we're just going to accept this one right here. This one's not really. It's one of those proofs where it's like you kind of grind through the computations and then you end up there, but you really haven't learned anything along the way. So we're just going to accept this formula here. These are going to be probably the most useful formulas for us to use for curvature. Probably this one maybe edges this one out by a little bit, but some people really like this one. So it's up to you which one you want to use. And so what we're going to do now is we're going to try to apply this, and we're going to find the curvature of a circle radius A. That's crossing, right? Yeah, this is the cross product because these are both vectors right here. That's right. So you need to do a cross product, which is why this might take a little bit of time. All right, find the curvature of a circle of radius A. All right, well, let's see here. Let's come up with the position function for a circle of radius A. Okay, so what do you think the x component of our curve is going to be? That's right. We're going to have the constant A, or the radius, times cosine of t. And that's going to be our x. And then y, of course, will end up being a sine of t right here. Anytime you want a circle, remember the x value corresponds to cosine and the y value corresponds to sine. All right, so what I'm going to do now, I'm going to go the number one route right here. I'm going to try to compute it this way, but you're welcome to try to do it this way. You should end up with the same answer. So we have r prime of t. So let's do the derivative here. Let's see, the derivative here is negative a sine of t. And then we have a cosine of t right here. All right, now what we want to do is we need to find out what this unit tangent vector is. And remember, the definition for that is our r prime, but then it's divided by its own magnitude. All right, so we already know what this is, so I guess we just need to figure out what the magnitude of r prime is going to be. All right, so remember the magnitude, the way we figured that out is we square each of the components and add them together. So I have a squared sine squared plus a squared cosine squared. Ah, this looks familiar. So we have something times sine squared plus something times cosine squared. That will just be the thing that's in front of them both. So this is the square root of a squared, which is absolute value of a, but we're assuming since it's a radius, this is going to be positive anyway. So we end up getting a for this. So that's going to be the magnitude, and normally this would depend on t, but for this particular example, it's always going to be a, no matter what the t value is. So anyways, now we could fill in what this is. So we have negative a sine of t, a cosine of t for the top, and then we divide by this magnitude down here, which is a. Now remember, a is a scalar, right? So if we want to divide this vector by a scalar, we just divide each of the components by that scalar. So we end up with negative sine of t, cosine of t, right here. Okay, so now we found our t hat, or our unit tangent vector. And then the last thing we need to figure out that we don't know yet is the derivative of that. So let's take a look. The derivative of this is going to be negative cosine of t, negative sine of t, right here. All right, so now we just need to do the magnitude of this divided by the magnitude of r prime, which we actually already know that. We figured that out earlier. So the bottom is just going to be a. So now we just need to figure out what the magnitude of the top is. All right, so let's see, what's that going to be? Yeah, I think you guys in the chat at least are already seeing it. So we have the square root, we have negative cosine squared, and then we have negative sine squared, and that's going to be 1. So our top value is going to be 1, and our bottom is going to be a. And this is going to be the curvature no matter where we are on the circle. And if you think about it, it makes sense. In a circle, you're always changing your direction at the same rate. So you're always kind of just directly rotating like this. And you're not really changing the speed at which you're rotating, like you're not having a steeper rotation or a shallower one. You're always rotating at the same speed. So this is going to be constant. Now, what does this mean? This means that the bigger the radius is, the smaller the curvature is. So imagine that we have this as a big circle. Notice that these are kind of shallow turns right here. We're not really bending that much right here. Whereas on the other hand, if we have a circle of small radius, our tangent vector is having to twist very frequently in order to keep up with this little circle here. So smaller circles have larger curvature and bigger circles have smaller curvature because smaller ones, you need to change your direction more quickly right here. All right. Now this one's a little bit of a fluke. In general, a lot of these will actually depend on t and they won't necessarily be constants. And we're actually going to see that in our next problem, if I'm not mistaken. So this one we got kind of a nice answer as a constant, but that won't always happen. Let's see, how are we doing on time here? Oh, we're doing pretty good. All right. So now what we're going to do is we're going to calculate the curvature of this curve right here. And again, I'm going to use the same definition for kappa. I think that ends up being the faster one, but if you're more comfortable with the other one, feel free to work with it on your own, and you should end up getting the same answer here. All right, so let's see. So our r of t is this, so let's see what r prime of t is. That's the first thing we need. Well, this derivative's not too hard. That's 2t. And then we do the derivative of this stuff. So the derivative of sine is going to be cosine. And then we do the derivative of this right here, which requires the product rule. The derivative of t will be 1. So I just have cosine of t. And then the derivative of cosine will be negative sine. And I leave the t alone. Oh, we're running out of room here. All right. And then now I'm going to do the derivative of this. So I have negative sine of t. And then I do the product rule here. I take the derivative of t and get sine of t left over. And then I have t cosine of t. Now with both of these, something very convenient happens. These cancel out and we're just left with t sine of t. And these cancel out and we're just left with t cosine of t. So that derivative actually kind of simplified things a bit, which is pretty nice. All right, next, remember our first objective is to get this t hat right here. So that's what we want to get first. And remember that t hat is r prime divided by its magnitude. Okay, so we need to know what the magnitude of this is. All right, let's see. So we do the square root. We have this component squared, which will be 4t squared. We have t sine of t squared right here. And so we have t squared sine squared of t right there. And then finally, we have this right here. All right, now once again, we got this nice Pythagorean pair going on. So can anyone tell me what the inside of this is going to, well, what's the whole thing going to simplify to? Do you guys see it? Yeah, so the inside of this at least will be 5t squared. And so I do the square root of that, and since t is positive, we have root 5t. So this is going to be the magnitude of our derivative. Okay, well then that means we come back here and we put an r prime. Just like that. So this is our r prime, and then we divide by square root of 5t. Okay, so let's see. Oh, conveniently, all of these have t's in them. That's very nice. So we end up with just 1 over root 5 times 2 sine of t cosine of t. And this is our t hat. Okay, so we ended up having a pretty nice t hat right here. All right, next we need to take the derivative of t hat and then find its magnitude. And then once we're done with that, we just put it in the formula and we're finished. So let's see, t hat prime, well, we're gonna have that constant there, 1 over root 5. The derivative of 2 is 0. The derivative of sine is cosine. And then the derivative of cosine is negative sine. All right. So now we need to find the magnitude of this right here. So let's see, that's the square root. Well, we don't have this anymore. And then we have cosine squared plus sine squared. So this is going to be 1 right here. But then remember that we also have this constant right here as well. We can't quite forget about that constant. And in general, the magnitude of a constant times a vector is the absolute value of that constant times the magnitude of the vector without it. So all in all, what this means is that the magnitude of t hat prime is going to be 1 over root 5. All right, good. So we got this far. And then now all we need to do to get kappa, or our curvature, is we put absolute value of t prime in the numerator. And then we put the magnitude of r prime in the denominator. And then we can simplify this right here. And we have 1 over 5t. And this is going to be our curvature. Now we conveniently avoided the issue that we were talking about earlier. So this function, 1 over 5t, does have a point where this is undefined at 0, but fortunately we're looking at this curve after 0, so we don't run into this issue right here. Effectively, we kind of, it's more or less sort of like the curvature version of a cusp, where we're turning infinitely fast for 1 split second. That's kind of what we're doing at t equals 0 if we looked at the curve there. All right, let's do one more example here, and then I think we'll be finished. Let's see here. Now, what happens if we just have a, let's say we go back in time to Calc 2 and we wanted to do curvature back then. Calc 2 is already full, so we don't have time to put curvature into that class. But what would we do if we wanted to compute curvature if we just had y equals f of x? Just a normal, not only a plane curve, but it's actually a function as well. Then there's actually a shortcut to getting the curvature when we look in Calc 1. Or sorry, Calc 2. Well, kind of Calc 1 as well. All right, so first of all, what we're going to do is we're going to write y equals f of x in this weird way. We're going to have r as a vector depending on x, and the x component is, well, x. I think that makes sense. And then the y component is f of x, because remember, y is equal to f of x. So here we have our position vector, and what that's doing is it's pointing to points on our curve right here. All right, now let's see what r prime is. Well, we do the derivative of x and get 1, and we do the derivative of f and get f prime. And then we take another derivative here, and the derivative of a constant will be 0, and then we have f double prime here. All right, now what I'm going to do is I'm going to use the, this is a time where the other formula for curvature will be convenient. So what I'm going to do now is I'm going to use this one that we had earlier, which is where we have r prime cross r double prime, and then we're going to divide by the magnitude of r prime cubed. All right, so let's do this cross product here. Let's see, I, j, k. All right, let's see, r prime. The formula for that is 1 f prime and then 0. All right, r double prime, well, we don't even have an I component. We have f double prime there, and we have 0 because we don't have any third dimension at all. All right, so let's see what the cross product is here. So for I, this is going to be our square right here, and we have f prime times 0, and then 0 times f double prime. Well, that's going to be 0. All right, then we have j. We have 1 times 0 minus 0 times 0. That's also going to be 0. And then finally for k, we actually might get something that's not 0. So we have 1 times f double prime minus 0 f prime right here. So we actually end up getting f double prime. Okay, so that is the cross product. And what's the magnitude of the cross product? Well, it's going to be the magnitude of this vector, so it'll be the absolute value of x double, or f double prime. So the acceleration kind of shows up here, and this is evidence that the curvature is not going to be acceleration here. Okay, now what we can do here is we can use our formula.
Professor.
Yeah, what's up?
Is that supposed to be r prime x cross r f double prime?
Oh, yeah, the prime got kind of absorbed into the arrow there. There we go.
Okay, thank you. I just wanted to make sure.
All right. Then we have r prime cubed. Okay, let's figure out what the magnitude of r prime is. Okay, so let's see. So that's the square root of the x component squared, so 1, plus the y component squared, so that's f prime of x squared. And then there is no z component. So this is the magnitude of r prime. Now remember, we're going to cube this, so our denominator ends up being 1 plus f prime of x squared. And if I cube a square root, this is the same thing as doing it to the 3/2 right here. All right, and then the top here, we already figured out what this is. This is absolute value of f double prime. So in the case where you're not even working in 3 dimensions, where you have just the normal R2 and you have a function instead, this is a shortcut to computing the curvature. This is definitely easier than writing everything in terms of the vectors here. Why is the denominator cube? Yeah, it's part of the formula and it comes out in the computation. Yeah, whenever you start seeing cubes in a formula, it's gonna get awkward. All right, so let's go ahead and apply this here. Let's find the curvature of the curve y equals ln of x at the point 1, 0. All right, why did the denominator become like that? Well, the magnitude of r prime is this right here, and then I was cubing it. And when I cube a square root, I have whatever's in there to the 3/2. All right, so let's see here. So y, which is f of x, is ln of x. And we need to know f prime and f double prime for this. So f prime is 1 over x. F double prime is -1 over x squared. And for this problem, it seems like our x is going to equal 1 right here. Okay, so let's figure out what kappa is. So this is going to be the magnitude of f double prime divided by this craziness on the bottom here. Squared to the 3/2. So many parentheses. All right, so now let's see here. So the magnitude of f double prime is the magnitude of -1 over x squared. Meanwhile, here on the bottom, I have 1 plus f prime squared, which is 1 over x squared, and then that's to the 3/2. All right, so this is my formula here. I could simplify it by having the absolute value, get rid of the negative here, but all I need to do really is just plug in 1. So if I plug 1 into here, I have -1 in absolute values, becomes a 1. And down here I have 1 plus, well, if I plug 1 into that, I'm going to get 1. So I end up with 1 over 2 to the 3/2. So this is going to be our curvature for this right here. Isn't f prime 1 over x? Yes, it is, and then we're squaring it right there. All right, so that's sort of a shortcut we can use when we have y as a function of x right there. All right, let's see. So next time we're going to conclude our study of these space curves, as they're called, by looking at what are called the normal and binormal vectors. So we're going to talk about that next time, and then that concludes the end of the first module, and that will be what our exam is going to be over. All right, did we finish in time here? Oh, perfect. All right. Well, anyways, I will see you all on Monday where we will talk about that. What was that?
Thank you.
Geez, it's not next week, but the week after, I think. Yeah, you guys have a good weekend too.
Thank you, Professor. Have a good weekend.
Oh, let me stop the recording. I always forget the recording.